In this lecture, we discuss curves defined by parametric equations. Imagine that you have this curve, C. For sure, this curve does not represent a function because it doesn't pass the vertical line test. For example, this vertical line intersects the curve in more than one point. That means it's not this C does not represent a function. Now, how to graph this, how to describe this curve? We can't describe this curve or write it in this form, y equals f of x, because it's not a function. Now, what should we do in this case? In this case, we define parametric equations that describe each point on this curve. So each point is defined as xy, but xy, if we just consider this as dependent and independent variable, I mean x and y, that means we can write it this way, y equals f of x, but that's impossible. So we need to define x and y in terms of a new, in terms of a parameter. Parameter, you can imagine parameter as a variable, but with some restrictions. But for the purposes of explaining the things, imagine that t is a variable. So t is called parameter, and that works as a variable that defines the function y and defines the function x, because in this case, if we write x as a function of t and y as a function of t, then we can determine any point on this curve C by determining some value of t. So t, if t represents time, which is the usual case, for example, when we consider time t equals 0, then we can find x at time 0 by just plugging 0. And then we plug 0 for y, for t, and the y formula, and then that gives us another value, and that will give me an ordered pair that lies on that curve C. So we can define C as the points x of t and y of t. X of t, this is now a function of t, and y of t is a function, another function of t, where t is real number, and sometimes we have some restrictions for t. Restrictions on t, like, for example, when we deal with angles, sometimes we make a restriction for t is between 0 and 2 pi, for example, and so on. Now let's take an example to show what we mean by all this. So we want to sketch and identify the curve by the parametric equations, the curve C by the parametric equations x equals t squared minus 2t and y equals t plus 1. Actually, we can write the x as x of t and y as y of t. Now, in this case, in order to graph this curve, we need to determine ordered pairs. Now, how to do that? As we can see, x and y both depend on the variable or the variable or parameter t. So we need to take some values of t. So t, and then find the corresponding values for x and y. So let's take t, -2, -1, 0, 1, 2, and 4. And then if t is -2, then x of -2 is -2 squared, 4, minus -2 times 2 is -4, that's equal to 8. and then y of -2 is -2 plus 1, -1. So this point is 8 and -1. And then we plug -1 to find x and y. X is 3 and y is 0. When we plug 0, we get 0, 1. When we plug 1, we get -1 and 2. When we plug 2, we get 0 and 3. If we plug 4, we get 16 minus 8, which is 8 and 5. Now we have these ordered pairs: 8, -1, 3, 0, 0, 1, -1, 2, 0, 3, 8, 5. After determining these ordered pairs, we can graph this curve. So to graph this curve, we have x-axis here and y-axis, and then we determine some values of or we plot these points. The points are 8, -1, 8 on x, 1, 2, 3, 4, 5, 6, 7, 8, and 8 and -1, we have -1, -2, -3. Here 1, 2, 3, -1, -2, -3, -4, -5, etc. So let's plot these points. So we have 8 and -1, 8 and -1. Where is this? Write it here. So we have 8 and -1. This point here, this is 8 and -1. And then 3 and 0. 3 on x and 0 on y. So this is 3 and 0. We have 0 and 1, 0 on x, 1 on y. -1 and 2. 0 and 3. And we have 8 and 5. 8 and 5 here. This is 8 and 5. And then we connect these points with a curve. So this is the graph of the curve C. This is the curve C. Now this point is at time -2. This is at time -1. This is time 0, time 1, time 2, time 4. So we could graph this function, this curve, sorry, by, this is not a function, doesn't pass the vertical line test. So we could use the parametric equations. These are called parametric equations. We use them to graph the curve C. Now we want to identify, this is the first part. We already sketched this curve. Now we want to identify it. I mean by identifying this, to determine whether the shape is, or the graph represents a parabola, for example, circle, any non-geometric figure. So how to do this? We know that the parametric equations were written as x equals t squared minus 2t and y equals t plus 1. Now it's easier to start from this. Let's write this in terms of t to find t. T is y minus 1. And if we know that t equals y minus 1, we just plug in here. We get x equals, instead of t, we have y minus 1 squared minus 2 times y minus 1. And then we simplify. This is y squared minus 2y plus 1 minus 2y plus 2. And then we simplify. So x is y squared minus 4y plus 3. As we can see, y is written as a function of y. It's a quadratic. This is a quadratic. That means, or I don't want to use the word function, but let's call this a quadratic equation. And then this is for sure parabola. This is parabola. So this is how we identify the curve. Let's take another example. Now, what curve is represented by the parametric equation x equals cosine t, y equals sine of t, where t is from 0 to 2 pi. Now in this case we start with what we have here. We have parametric equations x equals cosine and y equals sine, and since t represents angle from 0 to 2 pi, we can use some well-known trig identity. Sine squared plus cosine squared is equal to 1, and that represents actually the equation of a circle. So this is a good idea to start with when we have trig functions. It's a good idea to square x and square y and find the sum. So what is x squared? Is cosine squared t. What is y squared? Is sine squared t. But we know that cosine squared plus sine squared is equal to 1. This is an identity. So this represents, so we have x squared plus y squared equals 1, but this is the standard equation of the circle. So this is a circle of radius 1. Circle of radius 1. Now, if we want to know the direction, these curves are directed or oriented curves. So we have some direction on these curves because these we imagine that there's some point on this curve that moves as time changes. So how to graph this? Actually, for the previous example, this is the direction because it changes from t equals -2 to t -1 and so on. So as t increases, we are moving this way. For example, t0 is here, t1 is here, t2 is here. As you can see, this is the orientation. Now, what is the orientation of this? This is a circle. Is it clockwise or counterclockwise? Now, to determine that, we need to choose some points. So let's start with t equals 0. When t equals 0, we have xy becomes x of t, and y of t is x is cosine 0 and y is sine 0, but cosine of 0 is 1 and sine of 0 is 0. So the point is 1, 0. So this is the starting point, 1, 0, this point here. Let's see where we should go from that point. So let's use t equals, for example, 2 pi. When t equals 2 pi, we should get here, since this is circle, we get same point. But it's not clear what is the direction. So let's choose a point after 0. We have another point after 0. The other point, we can choose pi over 2. So cosine pi over 2 and sine pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So we move from this point 1, 0 to the point 0, 1, this point here. So that means this is the direction. It's counterclockwise. And if we determine the direction on one piece, that means it's the direction for the whole graph. So it's counterclockwise. This curve is called a closed curve. This is a closed curve because the starting point is the same as the end point. Starting point at 0 is the same as the end point at 2 pi. Let's take another example. If we want to find parametric equations for the circle with center hk and radius r. Now the parametric equations for a circle in standard form are x equals cosine t and y equals sine t, where t is between 0 and 2 pi. This is the standard circle. I mean circle centered at 0, 0, 0 at the origin. Now, if the center is not 0, 0, then we need to add h and k to these. So we get x equals h plus cosine t, but the radius changes. Here radius is equal to 1 and hk, the center, is 0, 0 for the standard case. But here the radius can be anything, so we multiply it by cosine, and y is k plus r sine t. This is a general form for a circle using parametric equations, where t is between 0 and 2 pi. And when we represent this, if we may get some circle here, so it's not on the center, is not the origin. Now let's take another example. We want to sketch the curve with parametric equations x equals sine t and y equals sine squared t. Okay, we want to graph that curve. So this is x, this is y, and in order to do so, we know that y equals sine squared, but sine is x, so we can write y in terms of x. So y equals sine squared t, and that's x squared. So y equals x squared is parabola. So the graph looks like this. This is y equals x squared. Now the direction is determined by some points. For example, the direction is the same. I mean, you can start from right to left or from left to right. So from here, this is the direction, and from here, this is the direction. Now let's deal with some or study some applications to calculus. So 10.2, let's talk about some calculus with parametric equations. And here, this is a wide topic. We have many applications. We can apply it to areas, apply it to surface area, apply it to arc length, many applications, but we will just try some problems, let's first write what the basic formulas that we need in applications if we want to apply parametric equations to calculus. So we need, the basic idea here is the derivative or the tangent line, the slope of the tangent line. So how to determine or to define derivatives? Let y equals f of x, where x is a parametric equation, so or parametric function or parametric equation. It's written in terms of t. Then using the chain rule, if we use the chain rule, then we get dy over dx or dy over dt, because we are working with respect to time t. This is dy over dx, because y is a function of x, but then the x is a function of t, so we multiply by dx over dt, because y is written in terms of x and x is written in terms of t. So if we want to reach t from y, so we first differentiate y with respect to x and then differentiate x with respect to t and multiply them. Okay, now we solve for dy over dx because we are interested in finding the tangent line. So dy over dx, I mean in terms of parametric equations. So dy over dx is dy over dt divided by dx over dt. We divide both sides by dx over dt, where this should be different from 0. We can't have dx over dt equals 0 because in that case the denominator becomes 0. So this is the first derivative. This enables us to find tangent line of a parametric curve with no need to eliminate the variable t. We can still have t, and we can find dy over dx, which is the parametric, the derivative or the slope of the tangent line. Also, we may need the second derivative of y with respect to x squared. This is the derivative of this, of the first derivative, dy over dx. So this is d over dt times dy over dx divided by dx over dt. So these are the formulas that we need. Now let's take some examples. If C, the curve C is defined as x equals t squared and y equals t cubed minus 3t, we want to find the two tangent lines of C at the point 3, 0. We have two tangent lines for this curve at specific point. So in this case, we need to find the derivative first. So what is the derivative of this function? Derivative, we are talking about tangent line. So dy over dx is dy over dt over dx over dt. So let's find dy over dt. dy, derivative of y with respect to t is 3t squared minus 3 over derivative dx over dt is 2t. So this is the slope of tangent line at any time t. Now, when x is, this point here is x and this is y. When x is equal to 3, we want to find the derivative at that point, at 3, 0. So when x is equal to 3, then 3 equals t squared, and that means t is equal to plus or minus square root 3. And then we find y of t. Y of plus or minus square root 3 is equal to square root, here we have plus or minus, cube minus 3 times square root 3 plus or minus. Now we have, this is plus or minus 3 to 1/3 minus 3 plus or minus 3 to 1/2 plus 1, which is 3/2. Now, what is y? Y is equal to 0. Y equals 0. So y of any point is 0. Y of plus or minus square root 3 should be 0. And that means C crosses, the curve C crosses itself at the point 3, 0. And actually the graph looks like this. The graph is not required, but if we graph this function using technology, we may get a graph that looks like this. This is a graph of the function. It can be written as y equals square root 3 times x minus 3. If we write y in terms of x, I mean finding t and plugging t that's written in terms of x here. So the graph looks like this, and the orientation is this way. And at the point 3, 0, this is 3, 0, we have two tangent lines, this one and this one. Now, the tangent line, if we want to find the tangent lines, we can find now the derivative dy over dx at t equals plus square root 3 is 3 times square root 3 squared minus 3 over 2 square root 3, plugging here. And then this gives us, after simplifying, we get, okay, so 3 times 3 minus 3, because square root 3 squared is 3, over 2 square root 3. This is 6 over 2 square root 3, which is 3 over square root 3. If we rationalize the denominator by multiplying by square root 3, we get 3 square root 3 over 3, and canceling these, we get square root 3. And we find the derivative evaluated at t equals negative square root 3, and that gives us 3 times negative square root 3 squared minus 3 over 2 square root 2 times negative square root 3, and this is 9 minus 3 is 6 over negative 2 square root 3, and that should give us negative square root 3. So the equations of these lines are y1 and y2. y1 is the slope square root 3 times x plus some point b1, and for the second one, the slope is negative square root 3 times x plus some point b2. Now, if we want to find b1 and b2, we just substitute the point 3, 0. So plugging 3, 0, we get, this is x, this is y. So let's substitute in equation 1. In 1, we have 0 equals 3 square root 3 plus b1, and that means b1 is negative 3 square root 3. And in equation 2, we have 0 equals negative 3 square root 3 plus b2, and that means b2 is negative 3 square root 3. Now that means the equations are the tangent lines. The equations for the tangent lines are y1 equals square root 3 x plus b1. b1 is negative 3 square root 3, and y2 is negative square root 3x plus b2, which is negative 3 square root. b2 is positive. because when we bring this here it becomes positive, so this is positive. So those are the equations of the tangent lines at the point 3, 0. Now part B, for the same problem, we want to find the points on the curve C where the tangent line is horizontal or vertical. Horizontal, the tangent line is horizontal. That means derivative with respect to x is equal to 0. And vertical, that means derivative does not exist. And that means the denominator should be equal to 0, because we know that dy over dx is dy over dt over dx over dt. If the denominator is 0, then it's a vertical line because it's undefined. So that means dx over dt is equal to 0. Okay, now let's apply the two cases. We have dy over dx equals 0. That means, what is dy over dx? dy over dx is this. It's 3t squared minus 3 over 2t. This is equal to 0 only if the numerator is equal to 0. And then solving for t, we get t squared equals 1, and that means t is plus or minus 1. So when t is 1, x is 1 and y is negative 2. 1 and negative 2 when t is equal to 1. When t equals negative 1, when t is equal to negative 1, x is negative 1 squared, which is 1. And y is negative 1 minus 3, which is plus 3. That gives plus 2. So the 2 points are 1, negative 2, and 1, 2. So these are the points on the curve C where the tangent line is horizontal. Now for the vertical case, we want dx over dt is equal to 0. Now dx over dt equals 0. X is t squared. So we differentiate with respect to t, we get 2t is equal to 0. That means t equals 0. And then we find the point xy. X is t squared. 0 squared is 0. Y is t cubed minus 3t. When we plug 0, we get 0. So the point 0, 0 is a point on the curve C where the tangent line is vertical. Now part C, we want to determine where the curve C is concave up or down. And that means when we talk about concavity, we are talking about the second derivative. And this is one of the applications with the second derivative. So as stated above, in this case, the second derivative y with respect to x is derivative with respect to t of dy over dx, all divided by dx over dt. So this is the formula that we need to use. We know that dy over dx is 3t squared minus 3 over 2t. Now, the second derivative of y with respect to x squared is d over dt times dy over dx is 3t squared minus 3 over 2t, all divided by dx over dt, which is 2t. Now we differentiate the numerator. Derivative of this is using the quotient rule, the denominator times derivative of the numerator minus numerator minus derivative of the denominator, all divided by denominator squared. Now over 2t. Now we simplify more, so we get 2t times 6t is 12t squared minus 2 times 3t squared is 6t squared, 2 times negative 3, and we have negative sign here, positive 6, over 4t squared, this is 4t squared, and then we flip the denominator, it becomes 1 over 2t. So we have 12t squared minus 6t squared plus 6 over 8t cubed. 6 over 8t cubed, and this is 6 times t squared plus 1 over 8t cubed. You can simplify to get 3 over 4. Now the numerator, this is not solvable, no 0 for this, so the numerator is not solvable. So the only case, because when we study the second derivative, we want the second derivative to study the sign and concavity. We need to determine the point where the function is either, or the second derivative has either derivative is equal to 0 or derivative does not exist. The second derivative is equal to 0 if the numerator is equal to 0, but that's impossible because we have sum of two squares, t squared and 1, and that's doesn't have a solution in the real numbers. So we don't need to worry about the numerator. What is the 0 of the denominator? The 0 of the denominator is the 0 itself. So the value of t that makes the denominator is equal to 0 is 0. Now we take some value greater than 0. Let's take t equals 1 and substitute it here. So we have 3 times 1 plus 1 over 4 times 1, that's positive. And let's try a value less than 0, like negative 1. We have 3 times 1 plus 1 over 4 times negative 1, this is less than 0. So this is concave down, this is concave up. And that means the function is concave up on this interval and concave down on this interval from negative infinity to 0. So we can write f is concave up, or the curve is concave up on negative infinity to 0, and the curve is concave down on 0 to infinity. Now let's take another example. If we want to find the tangent line to the cycloid that's defined as x equals r times theta minus sine theta and y equals r times 1 minus cosine theta at the point where theta equals pi over 3. Now for this problem, we need to find the slope. We need to find the slope. This slope is given by dy over dx equals dy. Now instead of t, we have theta. So we just change t to theta. So it's dy over d theta over dx over d theta. The parameter is theta. Now, what is derivative of y with respect to theta? With respect to theta, r is constant. What is derivative of 1 is 0. What is derivative of negative cosine is positive sine. So we have the derivative of y with respect to x is r with respect to theta is r sine theta. Now, what is derivative of x with respect to theta? This is x, derivative of x with respect to theta. What is derivative of theta? It's 1. Derivative of sine is cosine, and this is multiplied by r. And then we can cancel r to get sine theta over 1 minus cosine theta. Now, at theta equals pi over 3, when theta is equal to pi over 3, we have the slope dy over dx equals sine pi over 3 over 1 minus cosine pi over 3. But sine pi over 3 is square root 3 over 2, and cosine is 1/2. So we have square root 3 over 2 over 1/2, and that's just square root 3. So this is the slope. This is the slope. Now we need to find the 2 points x and y. So x is r cosine r times theta minus sine theta, and then we evaluate it at theta equals pi over 3. So we get r times pi over 3 minus sine pi over 3. This is r times pi over 3 minus square root 3 over 2. And then we find y. Y is r times 1 minus cosine theta. And this is r times 1 minus cosine pi over 3. This is r times 1 minus 1/2, which is equal to r times 1/2. This is equal to r over 2. Now we apply the formula equation, the formula for the equation of the tangent line. The equation of the tangent line is y minus y naught. Y naught can be considered as y, which is r over, so we can call this y naught. This is x naught, and this is theta naught. So specific theta, let's write it as theta naught. Now this is y minus r over 2, because this is y naught, equals, because you remember y minus y naught equals m times x minus x naught. M is the derivative. The derivative is, in this case, is square root 3 times x minus x naught. X naught is this point. So it's r times, this can be written as r pi over 3 minus r square root 3 over 2. So this is the equation of the tangent line. Now at part B, we want to find, let's make this part A, and now part B, we can find the points where the function is horizontal. B, at what point? Points is the tangent horizontal. Horizontal if the derivative dy over dx is equal to 0. So dy over dx is sine theta over 1 minus cosine theta. So sine theta over 1 minus cosine theta is equal to 0 only if the numerator is equal to 0. So in this case, if we're between 0 and 2 pi, theta is 0, pi, and 2 pi. Now let's take another example. Our last example here in this video is about the area. Find the area under one arc of the cycloid, x equals r times theta minus sine theta, and y equals r times 1 minus cosine theta. Now the graph of this looks like this. The graph of the cycloid between 0 and 2 pi r. This is 0, this is 2 pi r. Looks like this. So we want to find this area. Now to find this area, the area, if we restrict ourselves on theta from 0 to 2 pi, then the area in this case is given by the integral from 0 to 2 pi r y dx, but y is this expression. So this is 0 to 2 pi r times 1 minus cosine theta times dx. What is dx? dx is r times 1 minus cosine theta. We are differentiating with respect to theta, dx over d theta. And then we multiply this by d theta. We get r times 1 minus cosine theta d theta. And since we use theta from 0 to 2 pi, we don't need to write it as 2 pi r. It's from 0 to 2 pi, because here x is from 0 to 2 pi r. Now we convert it into theta, so theta is from 0 to 2 pi. Now we find this integral. So this is r times r is r squared. We can pull it out of the integral because it's constant. 1 minus cosine theta all squared d theta, and then we expand this. We get r squared times the integral from 0 to 2 pi, 1 minus 2 cosine theta plus cosine squared theta d theta. Now we find this integral. So r squared times, what is the integral of 1 with respect to theta? It's just theta. Now what is the integral of 2 cosine? It's 2 times, what's the integral of cosine? Is sine theta. Plus, what is the integral of cosine squared? Now let's find it here. Integral of cosine squared theta is the integral of 1/2 plus 1/2 cosine 2 theta. We can write it this way because we know that for cosine squared theta we have two main identities, 1 minus sine squared theta, and this is used if we have another term or another function multiplied by the cosine squared. For example, if it's multiplied by sine theta, we may use this, or sine squared, or so on. And we have the other one is 1/2 plus 1/2 cosine 2 theta. If we only have cosine squared inside the integral, we use this formula. So using this formula, what is the integral of 1/2? It's theta over 2. I mean 1/2 times theta, which is theta over 2, plus 1/2. What is integral of cosine 2 theta? We multiply by the reciprocal of the coefficient of theta, 1 over 2, times what is the integral of cosine? It's just sine 2 theta. Now we put this here. We have theta over 2 plus 1/4 sine 2 theta. And this is from 0 to 2 pi. Now we can erase this. Now we substitute 2 pi. We have r squared times 2 pi minus 2 sine 2 pi plus 2 pi over 2 plus 1/4 sine 4 pi minus r squared times, now we substitute 0. 0 times 0 minus 2 sine 0 plus 0 over 2 plus 1/4 sine 2 0. Now this is 0. Now what about the first part? We have r squared times 2 pi. This is 0. This is 0 plus pi, and that's 3 pi r.